Okay, so this is the second video for section 4.1 in AP Calculus on extreme values of functions. Here we're going to pick up with example 2 that wants us to find the extreme values of f of x equals 1 over the square root of 4 minus x squared. So when they say extreme values, that could mean absolute or local extreme values, so all of them. So to begin with, what we need to do is we need to find the domain for the function to see would this be a closed interval or would this be a domain of all real numbers, in which case they could be any open interval. So if I look at the function there, I notice a couple of things. I notice first off that it's a rational function. So remember, a rational function could not exist whenever the denominator is equal to 0. So I need to see if that could possibly occur. So if I square both sides, get rid of the radical, and then add the x squared to the other side, and when I square root that, I get plus or minus 2. So what I now know is that positive and negative 2 could not be in the domain of this function, because if I was to substitute those x values in, I would end up with 0 in the denominator. The other thing that I notice is that I have a square root in my function, and I know that I cannot take the square root of a negative. So in fact, I need what's under the radical to be greater than 0. So that I'm square rooting something that's positive and not equal to 0, because I already know from the fact that it's in the denominator that it can't be 0. So that means negative x squared has to be greater than negative 4. X squared has to be less than positive 4. So when you square root that, you get plus or minus 2. But how does your inequality work? Well, here's negative 2, here's positive 2. The question is, would you use x values between negative 2 and positive 2, or outside of them, like positive 3, positive 4, negative 3, negative 4? Well, in order for x squared to be less than 4, my x values need to be smaller than 2, which means that they would need to be greater than negative 2. So my domain is from negative 2 to positive 2. Notice that that is not a closed interval. If it was a closed interval, I would be using brackets, and I would actually be including negative 2 and positive 2 as the endpoints of my domain. But I know from over here that I cannot actually include negative 2 and positive 2. So if I would end up with a max or min at negative 2 or positive 2, I can't actually use that as an answer because it's not actually part of my function. So to answer this, our domain is not a closed interval. It is the open interval from negative 2 to positive 2. So moving on then, I know that all of my maxes and mins should be contained between x values of negative 2 to positive 2. So then I'm going to approach it the same way that I approached the first example in the first video. I'm going to find the first derivative. So my original function was 1 over the square root of 4 minus x squared. I'm going to rewrite that a little bit before I go try to take the derivative. So this would be 1 over 4 minus x squared to the 1/2, or 4 minus x squared to the negative 1/2. If I write it that way, then I can just use the chain rule to evaluate the derivative rather than having to use the quotient rule and the chain rule at the same time. So that means that my derivative would be taking power in front. My new exponent, if I subtract 1, which means I subtract 2 over 2, my new exponent is negative 3/5, and then I can't forget about the derivative of the inside. Now I need to clean that up in order to be able to use it for step 2. So these are not really quit while you're ahead type problems. So to clean it up, the negative 1/2 and the negative 2x can be multiplied together to give you a positive x. The 4 minus x squared to the negative 3/2 we can move to the denominator to make it a positive 3/2. So your derivative would be x over 4 minus x squared to the positive 3/2. So then we're going to use that to do step 2 of finding the critical points. Remember, the critical points are wherever the derivative is equal to 0 or does not exist. So the first thing I'm going to do is setting my derivative equal to 0. Doing that, you would take the denominator, multiply it to the right-hand side, but since it's times 0, we would just get x equals 0. So x equals 0 is the location of one critical point. The other thing we need to look at is when the derivative does not exist. So being that this is a fraction again, it's not going to exist whenever the denominator is equal to 0. So to get rid of this, we have to raise both sides to the reciprocal of that. So this will become 4 minus x squared. 0 to anything is just going to be 0. And so we get plus or minus 2. However, we know that positive and negative 2 are not actually in the domain of the function. So we only have one critical point, and that is at x equals 0. So using that, we then move on to step 3 to determine whether at x equals 0 we would have a maximum value or a minimum value. So that is where we create what's called a sign line, or sometimes you hear it called a wiggle graph. Basically a number line. The only thing you put on the number line are your critical points. So for this one, the only thing I'm going to put on it is that x value of 0. I'm going to label the number line with the function that I'm evaluating it for, which would be f prime. What we're going to be doing is we're going to be checking our derivative to see if to the left and to the right of my critical point, whether my derivative is positive or negative, because that would tell me whether my graph goes from increasing to decreasing or decreasing to increasing. So to do that, you're simply going to pick any number in that interval of the number line and substitute it into your derivative. So for this first one over here, I could choose -1. So I would evaluate f prime of -1. To do that, my derivative was x over 4 minus x squared to the 3/2. Now, I don't actually care what this number is. I just care would it be a positive answer or a negative answer. So you don't have to do a ton of math involved here. As long as you show your substitution there, and then show whether that would be a positive or a negative answer, even if you can't really think it through all the way, or if it's a complicated number that you can end up with. As long as you can determine positive or negative, that's all they're really looking for from you. So obviously the numerator is going to be a -1. The denominator, -1 squared is +1. 4 minus 1 is 3. So I would have 3 to the 3/2, which is going to be a positive number. So I've got a negative number in the numerator divided by a positive number in the denominator. So that's going to be less than 0. So I'm going to label my sign line up there. And that's S-I-G-N, not S-I-N-E. I'm going to label that with a negative. So I know that my original graph would be decreasing until I get to this x value of 0. Now I need to make sure, though, that on the other side of 0, that I have positive derivative values to show that my graph would go to increasing. It's possible that it's decreasing and it continues to decrease, which would mean that x equals 0 is not a max or min of any kind. So I do still have to check the other side of my sign line as well. So I'm just going to substitute +1 in for that one. So that would be x over 4 minus x squared to the 3/2. So we end up with +1 over 3 to the 3/2. Positive divided by positive gives us a positive number, which would tell me that my original graph would go to increasing there. So that means that I would have an absolute minimum, because it is absolutely the lowest the graph would ever go, at an x value of 0. But they asked for the directions at the beginning of the problem where to find the extreme values. Values are always y coordinates. You can include the x, like I included the x value of 0, but you absolutely have to include the y coordinates, unless they specifically say find the x coordinates of the absolute mins or maxes, or however they phrase it. But if they don't specify x coordinates, then you absolutely need the y coordinates of your answer. So to get the y coordinate, we would need to take our x value for our critical point and substitute it into the original function. So that would be 1 over the square root of 4 minus 0 squared. So you get 1 over the square root of 4, which is 1 half. So I have no maximums of any kind. No absolute maximums, no relative maximums. All I have is a single absolute minimum at 0, 1/2 for this particular function. So it's important that you understand that while a function's extrema only occur at critical points or at endpoints, not every critical point or endpoint signals the existence of an extreme value. So just because it's a critical point or just because it's an endpoint, that doesn't mean that it has to be a max or min. That's why the sign line is so very important, to make sure that we really do change from increasing to decreasing or decreasing to increasing at those particular critical points. So that leads us into example 3 here. Example 3 wants us to identify the critical point and determine the local extreme values. So our process is going to be the same as both for example 1 and example 2. For f of x here, I know that this domain would be all real numbers, including 2, because we actually include it in the first piece of our piecewise here. So my step after determining the domain is to find the derivative of the function. So the derivative of the function, I would take the derivative of each piece of the piecewise. So the derivative of the first piece would be 3x squared minus 2, and the second would be 1. This one would apply for when x is greater than 2. This one would apply for x is less than 2, but the question is, does it also apply for equal to 2, like the original function did where it included 2? So to check that real quick, you would simply substitute 2 into both pieces of the piecewise, both into the original function to ensure that it's continuous, and then if it is continuous, into the derivative to make sure the derivative pieces would match. So if we look at f of 2 would be 2 cubed minus 2 times 2, so that's 8 minus 2 is 4. And then x plus 2 would be 2 plus 2.
Teachers, please pardon the interruption.
So we know that the function is continuous at 2. Then if we check in the derivatives, if I substitute 2 into both pieces of the derivative, 3 times 2 squared would be 3 times 4, which is 12, minus 2 is 10, which does not equal 1. Therefore, the slopes would not match up at x equals 2. So x equals 2 is a place where my derivative actually does not exist. That means that when it comes to critical points, x equals 2 is going to be a critical point. So if I kind of keep a list of critical points, x equals 2 is going to be one of them. The other places I would have critical points would then be anywhere else that my derivative does not exist, which doesn't happen here, or wherever my derivative equals 0. So you would want to look at both pieces of the piecewise. And so you get x equals plus or minus the square root of 2/3, as weird as those are. So x equals negative square root of 2/3, and x equals positive square root of 2/3 are going to be critical points. And as far as setting the second piece of the derivative equal to 0, 1 is never going to equal 0, so we don't get anything from there. So I have 3 critical points, and then I just need to identify if those are going to be maxes or mins. So from there, I would need to create a sign line for my derivative, and the only things I put on it are those 3 numbers. So I would have the negative square root of 2/3, and then in order, I would come to the positive square root of 2/3 before I come to 2 there. All right, so then you would substitute numbers in all 4 sections of that number line. So I will go ahead and tell you that when you do that, you should get positive, negative, positive, positive. So what that means is that my original graph goes up, down, up, and up some more. So what that tells me is that I would have a local max at an x value of negative square root of 2/3. We'll worry about the y value in a minute. I would have a local min at positive square root of 2/3. And here at 2, it increases to 2 and it continues to increase after 2. So 2 actually does not end up being a max or min of any kind there. To get your y values that go with those maxes or mins, you would substitute back into the original piecewise function over here. And both of those would fall into the first piece of the piecewise. So I'll go ahead and tell you what your answers would be for that. You would get 4 times the square root of 6 over 9 and negative 4 times the square root of 6 over 9 for your local max and local min for that function. So that wraps up example 3. Our next video, we make one final third video for this that's going to cover examples 4 and 5 from your notes.